Your model is trained, packaged, and live behind an API. You might think the hard part is over. It isn't. A model learns a snapshot of the world, and then the world keeps moving. This is drift, and if you don't watch for it, your model quietly gets worse. Here's the tension in one picture. The model is frozen the moment training ends. Call it week 0. It never changes on its own. But week after week, the data flowing into it does change. The model stays still while the world drifts out from under it. Let's make that concrete with one feature: applicant income. When we trained, incomes looked like this, a spread centered around 60,000. This is our reference, the world the model learned. Now here's the same feature a few weeks later, during a downturn. The whole distribution has slid to the left, many more low-income applicants, far fewer high earners. The model is still expecting the old picture. This mismatch is called data drift. Eyeballing histograms doesn't scale. We want a single number for how much did this shift. That number is the Population Stability Index, or PSI. For each income band, we take how much its share changed, times the log of the ratio, and add those up across all the bands. Let's actually add them up. Each band contributes a little as we go. The ones that change the most contribute the most. And the total lands at 0.56. Is that a lot? There's a rule of thumb. Below 0.1, the population is stable. Between 0.1 and 0.25, moderate, worth watching. Above 0.25, a significant shift, go investigate. Ours is 0.56, well past that line. And notice, we detected all of this without a single new label. Why do we care about the inputs so much? Because of what happens to the thing we actually sell: accuracy. Here's the model's accuracy. Week by week, as the drift builds, it starts near 76% and slides down to about 51, a drop of 25 points, and nobody changed a line of code. It rotted silently. Two different things are happening, and it helps to name them. On the left, data drift, the inputs moved. That's what PSI caught. On the right, concept drift, the relationship between the inputs and the answer changed. The true decision boundary rotated away, while the model's boundary stayed frozen. Data drift you can see in the inputs. Concept drift you can't. It only shows up when accuracy falls. And here's the painful part. The true label, did this loan get repaid or default, often arrives months later. By the time accuracy tells you there's a problem, you've been making bad decisions for weeks. So watch what you can see immediately. The model's own output. As incomes fell, its approval rate slid down too. That falling output is prediction drift, an early warning you get for free, long before the labels come in. Put it together, and monitoring watches three signals: the inputs, PSI on each feature; the outputs, the score distribution; and accuracy against true labels, which is the ground truth but always lags. The first two are your early warning system. We set a simple alert, PSI above 0.25. On this data, it would have fired all the way back at week 2. When that alarm is real, the response is a short loop. First, investigate. Is this a genuine shift in the world, or just a broken data pipeline? If it's real, retrain the model on fresh, recent data, then redeploy it as a new version. And that retrain and version loop is exactly what we'll build next. To recap, a deployed model decays as the world changes. Data drift means the inputs moved. Catch it with PSI, no labels required. Concept drift means the input to output rule moved. You see it as falling accuracy. And because labels lag, you watch inputs and outputs as your early warning. Detecting drift is only half the job. Next, we respond to it, retraining and versioning.